Hey all dear friends, this is Prajesh Chaudhary Quantum Group. Let's see this question of Irodov from Hydrodynamics. It's a question number 1.315. It's a simple conceptual question. Question states ideal fluid flows along a flat tube of constant cross section located in a horizontal plane and bent as shown in the figure. The flow is steady. Are the pressures and velocity of the fluid equal at points 1 and 2, and what is the shape of the streamline? So this is an horizontal plane and it is the top view, so there is no role of gravity here. We can divide the pipe into three parts. This part is up to here, that is straight part, and this is also straight part, and this is circle. So according to the shape of the pipe, the fluid will flow. So streamline on this part would be straight line like this, and a streamline on this part will also be straight like this, and the streamline here will bend according to the shape of the pipe. So the shape of a streamline on this part would be circular. Now the question is whether pressure at point 1 and 2 would be more or not, where it will be more, where it will be less, and same for the velocity. Alright, so for this part I want to take a little section, little mass of the fluid, something like this. And obviously for this part always there will be some mass dm here, and through this part we can take an average velocity v, and this is a part of a circle, so its center is somewhere here, so that is r. So its dm mass, or say mass m, is moving with velocity v on a circle, so it has to have a force mv square by r towards the center. And from where we'll get that force? We'll get that force from the pressure. So if pressure at A is say P1, pressure at 1 is P1, pressure at 2 is P2. So by virtue of the pressure, so here the force will be P1. Suppose this section area I have taken A, so that is a P1A, and here that is P2A, and if mass of this part is m, so we can simply write equation of motion P1 minus P2, A is equal to m V average square divided by RC. Obviously this is a positive thing, this is a positive thing, so P1 has to be greater than P2. So that is clear. Pressure at point 1 should be greater than at point 2. And now about the velocity part. So an ideal fluid is also irrotational. What do you mean by irrotational? Irrotational means it does not form any vortex. Understand vortex? Vortex is whirling kind of thing. So there is no rotational part along a closed path. So if it is a irrotational, so along any closed path, line integral of velocity is 0. So that is the condition of being irrotational. So v dot dl is 0 along a closed path. So here suppose this is the center. This is, first of all, from here circular path is from here to here. Alright, and the center of circle is here. So if I take a closed loop like this, this is the closed loop I am taking. This closed loop is A, B, C, D. On this closed loop I will apply this v dot dl integral summation to be 0. So on this part, suppose the velocity on here is v1, and velocity here would be something, velocity here is v2, and velocity here would be something. You see that the dot product of v dot dl on AB and CD would be 0, and v dot dl on BC would be, so the velocity vectors are parallel to BC, so that will be simply v1 into BC. So that would be v1 BC, and here v2 is opposite to the element dl here, so that will be minus v2 into dA, and that whole thing is 0. So v1 by v2 is equal to v1 by v2 is equal to dA by BC. You can see that dA is smaller than BC, so that is less than 1. So v1 is smaller than v2, right?